In this video, we're going to start looking at solving trig equations. So in the first handful of examples, we're going to try to find solutions just in the interval of 0 to 2 pi. Cosine of x equals square root of 3 over 2. Thinking about where on the unit circle, again, 0 to 2 pi is just one revolution of our unit circle. Where do we have cosine equal to square root of 3 over 2? We know that cosine is positive in the first and the fourth quadrants, and cosine's the x value. So if we think about those triangles, we want a longer horizontal segment than the vertical segment. So that takes us to pi over 6. And we're going from 0 to 2 pi. So if you have just recently watched the video on our inverse trig functions, we would think of this angle in the fourth quadrant as maybe negative pi over 6. But because we are looking at the interval from 0 to 2 pi, they're defining that. We are going to keep that as 7 pi over 6. Two cotangent x plus 1 equals -1. We're going to start isolating our trig function just like we would if we were just trying to isolate a variable. We're going to subtract 1 first. Subtracting 1 from both sides, 2 cotangent x equals -2. And then we're going to divide both sides by 2. So we have cotangent x equals -1. And we want to think about the reciprocal function. Cotangent's reciprocal is tangent. So that means that tangent of x is also equal to -1. Now, if we think about our unit circle, where does tangent equal -1? That's going to be in our second and our fourth quadrants at those perfect diagonals. That's going to be 3 pi over 4 and 7 pi over 4. Cosecant squared theta minus 2 cotangent theta equals 0. Notice we've got two different trig functions here. We want to work to get them in terms of one trig function. So I'm going to use my Pythagorean identity for cosecant squared theta. I know that cosecant squared theta is 1 plus cotangent squared theta minus 2 cotangent theta equals 0. And if we look at this, we've got a trig function squared and then a linear trig function or another trig function to the power of 1. We want to start recognizing that this is in quadratic form. And when we're using, or when we have an equation in quadratic form, we sometimes use a technique called U substitution to help us make the equation look a little bit easier to solve. So I'm going to let U equal cotangent x. So if I substitute now in U everywhere I see a cotangent x, I've got 1 plus U squared minus 2U equals 0. And I can rearrange the left-hand side. So we've got U squared minus 2U plus 1 equals 0. And now this looks really straightforward. It's not as complex looking. It looks like a normal quadratic that we are going to try to factor. So my first terms in my binomials have to be U because they multiply to give me U squared. And then my last terms need to multiply to give me 1. So 1 and 1. Now I need to think about the signs. If the middle term is a -2U, I need a minus 1U and another minus 1U. And now those signs, double checking that last term, that -1 times -1 does equal +1. We are good to go. We factored this correctly. Since both of these factors are the same, we don't need to set them both equal to 0. We can just set the one equal to 0. So we can solve that U is equal to 1. Now, a common mistake is stopping here. But remember, if we look at our original equation, our variable wasn't U, it was theta. So now we need to back substitute. So U, we said, was cotangent of theta. Oops. I misidentified, this should be theta over here. Make sure you're using the same variable that's given in the original problem. So cotangent theta is equal to 1. Using that reciprocal property, cotangent theta equals 1 tells me that tangent theta, which is the reciprocal of cotangent, is also 1. Now thinking about the unit circle, tangent's positive in the first and the third quadrant. And to get a ratio of 1 with sine over cosine, those values for sine and cosine have to be the same. So that's going to be pi over 4 and 5 pi over 4. Excuse me. Secant squared theta plus 2 equals -1. We're going to isolate that secant squared function by subtracting 2 from both sides. And if I go to take the square root of both sides, the left-hand side is going to simplify to secant of x, but I can't take the square root of -3 without it being imaginary. So this is an imaginary solution, which means there's no solution. And I've introduced a new symbol for therefore. It's 3 dots in the shape of a triangle, and it just translates to therefore. You see that in a lot of proofs in upper level math classes. Secant squared theta times tangent theta equals 2 tangent theta. I'm going to start by setting this equal to 0, subtracting 2 tangent theta from both sides. You want to be really careful. When you're solving an equation, you do not want to divide by a variable to try to simplify. I've seen students start this problem by trying to divide both sides by tangent of theta, but you're getting rid of one of these factors. So you're going to end up missing a solution. So make sure when you're solving an equation, you don't start by dividing by any variables. So now we want to factor out tangent theta, since both of our terms have a factor of tangent theta. We've got tangent theta times secant squared theta minus 2 equals 0. And our zero product property now lets me solve each of these factors equal to 0. So tangent theta equals 0. And secant squared theta minus 2 equals 0. Starting with tangent theta equals 0. Remember that tangent theta is equal to sine theta divided by cosine theta. And in order for this ratio, sine theta over cosine theta, to be 0, that means sine theta has to be 0. And sine theta is 0 at theta is equal to 0 and pi. Now we're not done solving. We need to also look at the next equation, secant squared theta minus 2 equals 0. We're going to add 2 to both sides. So secant squared theta is equal to 2. We're going to take the square root of both sides. And when we take the square root when we're solving, we need to add the plus or minus. So secant theta is equal to plus or minus the square root of 2. Secant theta using our reciprocal identities is 1 over cosine theta. Which, let me follow through with this thought, equals plus or minus the square root of 2. If we cross multiply, what this gives us is that cosine theta is equal to plus or minus 1 over the square root of 2. We could have started that anyway by saying if secant theta equals plus or minus the square root of 2, then cosine of theta is the reciprocal of that. It just wasn't where my brain was headed in this moment. Let's rationalize this denominator to hopefully see a value we're familiar with. So multiply by the square root of 2 over 2. We're finding where cosine theta is equal to plus or minus square root of 2 over 2. Thinking about my unit circle, since we're looking at both positive and negative values for cosine, we're looking at all 4 quadrants. And that's going to be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So we actually have 6 solutions for this equation. We have 0 and pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Tangent theta minus cotangent theta equals 0. I'm going to rewrite cotangent theta in terms of tangent theta. So we have tangent theta minus 1 over tangent theta equals 0. Now I'm going to get a I'm going to clear out this rational function by multiplying everything by tangent theta. So I'm going to distribute tangent theta to all 3 of these terms, leaving me with tangent squared theta minus 1 equals 0. Subtracting 1 from both sides, tangent squared theta equals 1. Taking the square root of both sides, adding our plus or minus, tangent theta is equal to plus or minus 1. So we're, again, looking at plus or minus values for tangent function. We're going to be in all 4 quadrants. The only place where we get a ratio of 1 for tangent is when sine and cosine are the same. So that's going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. This equation could also be set up if we were to convert both tangent and cotangent into expressions involving sine and cosine. You could solve it that way as well, getting the same solutions. It is a bit lengthier of a process, though. Solve the following in the interval from 0 to 360 degrees. Quick observation, now we're changing our units for our angle. So now we're looking in degrees. We're going to round our answers to the nearest tenth of a degree. Those directions of rounding your answers to the nearest tenth does indicate that we're probably going to end up using our calculator. 9 sine squared theta minus 6 sine theta equals 1. I'm going to subtract 1 from both sides. Setting this equal to 0, and again, hopefully recognizing that this is in quadratic form. So we're going to use that u substitution technique. I'm going to let u be sine of theta. So now I have 9u squared minus 6u minus 1 equals 0. And anytime I have a quadratic trinomial, I'm going to try factoring first just to see if it will work. Factoring is generally a little bit more straightforward than, say, using the quadratic formula. So my first 2 terms in the binomials need to be factors of 9u. So we could do 9u and u. And then my last two terms in my binomials need to be factors of 1, so just 1 and 1. So thinking about that outer and inner, seeing if there's any way to get minus 6u, I could do 9 and 1. 9 and 1, regardless of the signs, are never going to give me 6. So that didn't work. We could also try 3u and 3u, 1 and 1. 3u for my outer, 3u for my inner. This might work, but now we need to be careful of signs. My last two terms need to multiply to give me -1, which means one of them has to be positive and one of them has to be negative, which is going to make that inner term cancel out. So this does not work either. So after 2 attempts, and I don't know any other factors of 9u squared, I'm going to call this a wash and transition to the quadratic formula. The quadratic formula is usually u or x equals, but because our variable here is u, it's u equals -b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. Simplifying underneath the radical, -6 squared is 36. -4 times 9 times -1 is another 36 divided by 18. 6 plus or minus. I'm going to rewrite this in a very special way just to help us simplify this. But this is 2 times 36. So 36 plus 36 is 2 times 36 over 18. And the reason I'm going to do that is because 36 is a perfect square. So now that I have a factor that's a perfect square, I can bring that out of the radical. So we've got u is equal to 6 plus or minus the square root of 36 is 6 times the square root of 2 over 18. From here, we want to simplify even further. There's a couple of shortcuts for this. I'm going to show this very formally just to make sure that we see that there is a factor of 6 in all of these terms, which is what's going to simplify out. So I'm going to factor out 6 for my numerator, 1 plus or minus the square root of 2 divided by 18. And now I'm going to simplify the 6 over the 18. So we have that u is equal to 1 plus or minus the square root of 2 divided by 3. Now we have u, not our variable. U, remember, was representing sine of theta. So we have sine of theta is equal to 1 plus the square root of 2 over 3. And we have sine theta equals 1 minus square root of 2 over 3. Looking at the equation on the right, we're going to use our inverse trig function or inverse sine. Theta is equal to inverse sine of 1 plus square root of 2 over 3. Which, if we type this into our calculator, again, checking that we're in degrees, we want to make sure that we've got the right mode set up. So check that on your calculator. We get 53.6 degrees. Inverse sine, if you recall, is only going to give us a value, an output in quadrant 4 or quadrant 1. But sine is an odd function. So we're going to see some repetition of this value of theta and this corresponding sine value of 1 plus square root of 2 over 3. So if I visualize, my 53 over 53.6 degrees is in this first quadrant, say here. Well, if I were to mirror that about the y-axis on the unit circle, that terminal side is going to have that same y value for sine. So this first angle in the quadrant in quadrant 1 is 53.6. Again, thinking about mirroring that, we can see that the that's going to be the reference angle for our second measure of theta. So if that reference angle is 53.6, to find our missing angle or our additional angle, we're going to subtract 53.6 from 180. Which is 126.4 degrees. So my first equation gave me two solutions. Now we need to look at the next equation, sine theta equals 1 minus square root of 2 over 3. Setting this up the same way using inverse sine, theta is equal to sine inverse of 1 minus square root of 2 over 3. And if we evaluate this in our calculator, we get negative 7.9 degrees. Again, inverse trig functions, inverse sine in particular, is going to always give us an output from negative pi over 2 to pi over 2, or in this case, negative 90 degrees to 90 degrees. So this negative 7.9 degrees, that terminal side is going to be in the fourth quadrant. Our angle theta, we do want a standard angle from 0 to 360 degrees. So negative 7.9 isn't going to be our solution. We need to take 360 and subtract 7.9. Just 352.1 degrees. And similarly, if we reflect that terminal side about the y-axis, we're going to have another point that has the same y value. And that reference angle is going to be 7.9 degrees. So to find our second measure of theta, we're going to take 180 and add 7.9. So 187.9 degrees. So we had 4 angle measures that were solutions to this equation. And our last example, we're telling you now that we're not going to be able to solve this by hand, so we're going to use a graphing calculator to solve. And this is really not intended to be instructional in terms of this is how you should solve every trig equation, but just to illustrate how we can use a graph to solve equations that we can't solve by hand. So we have x times sine of x minus 5 sine of x plus 4 equals 3 on the interval from 0 to 2 pi. In my opinion, it's easiest to solve equations using a graphing calculator or using the graph if we have it set to 0. So we're going to subtract 3 from both sides. So we have x times sine of x minus 5 sine of x plus 1 equals 0. This isn't linear, this isn't quadratic, so none of the techniques that we have that we already are really familiar with and very comfortable with are going to work to solve this equation. So that's why we're going to go to Desmos to look at the graph. All right, so in Desmos, we're going to type in the left side of that equation. So x times sine of x minus 5 sine of x plus 1. So certainly a pretty wonky looking graph. I'm going to check one thing before I go any further. My interval was from 0 to 2 pi, so that implies we want radians. So I just want to make sure that I've got radians set up here. And we only want from 0 to 2 pi, so I can actually further set this up. So my x-axis can be 0 to 2 pi. And that's going to highlight the values that I actually want to look at. Because if you think about that previous graph, there were a lot of different places that we might be looking at. Now, we have it set up that this equation we have graphed is set equal to 0. Well, if we set something equal to 0, what that finds is our x-intercepts, which is why I wanted to make sure that I isolated my graph to only the window that I wanted to look at, so I can find my two solutions. If I click on my graph, Desmos will give me that exact solution. So I can see that x is equal to 0.21. And then I can also look at this other point. That's 2.693. So those are the two solutions for this equation that we wouldn't be able to graph or solve that equation by hand. Again, I can't stress this enough. Please make sure that you're not just defaulting to this technique as a way to solve equations. You are going to be expected to solve an equation by hand if it is something that's in our skill set. So just be mindful of that. This shouldn't be your first go-to in terms of getting these solutions.